Smile. It's time for calculus. All right. Fundamental theorem of calculus, part 2. Man, the sequel is almost better than the original. When does that ever happen? So we're going to work through some fundamental theorem of calculus part 2 questions today, right? You're going to be asked to take derivative of an integral function, right? An integral function that accumulates the area under a different curve, right? This idea of the fundamental theorem of calculus involving an antiderivative, which was so important to the fundamental theorem part 1, being able to evaluate a definite integral. We can actually use that fundamental theorem of calculus part 1 as we explore the ideas of integral functions, like being able to take derivatives of functions, being able to talk about the concavity of functions, right? We need to be able to take the derivative of these integral functions. So if you can kind of imagine if a definite integral involves this antiderivative, and we're going to turn around and take the derivative of it, it's not surprising that the fundamental theorem of calculus part 2 says that the derivative of an integral expression is just the same integrand function that we started with. Okay, so let me think about it this way, right? If we think about it with the fundamental theorem of calculus part 1, the integral from a to x of f of t dt, if we apply the fundamental theorem of calculus part 1, right, we're going to have to find an antiderivative of that function and then sub in our two limits, a and x. So I can simply rewrite that as antiderivative of a cap f at x minus cap f at a. So really I've rewritten the integral without an integral, right? But it's involved this antiderivative, capturing this antiderivative. Sometimes I can do that. Sometimes I can't. Sometimes I forget what the antiderivative rules are. Sometimes I just am lost. All right. But if I use this idea of cap f, it's just this idea of the antiderivative. So let's not get too caught up right now in finding that antiderivative f. Let's think about where we're going with it. Okay. So we're saying that this definite integral here, this definite integral function, right, is in terms of x because t is just a space holder for the limits x and a. So we've rewritten the definite integral, and t has disappeared because it's just holding the place for the two limits, a and x. So it's a function in terms of x. F at x is a function of x. Now, what's f of a? F of a, any function with a constant plugged in, is a constant. Okay, so what we're going to be asked to do is to take the derivative with respect to x of this integral from a to x of f of t dt. But it's the same as taking the derivative of the expression that is cap f of x minus cap f of a. And what is the derivative of the antiderivative? We're just kind of like undoing it, aren't we? The derivative of the antiderivative big F is just back to the original little f. That's why it's little f at x. And the antiderivative of a bit, wait a second, that's a constant. And the derivative of a constant is 0. So the derivative of cap f of x minus cap f of a with respect to x is just little f of x. It's the original function f, but now it's not in terms of this dummy variable t, it's in terms of x. Now, how is that different if the integral is to a function, right? So look at using the chain rule. Chain rule is the derivative rule that is always in play. It's always in play. You could be doing power rule, you could be doing trig, you could be doing, it doesn't matter because the chain rule always happens. It always happens. So if we could rewrite the integral that is from a to a function g of x of little f of t dt using the fundamental theorem of calculus, right, it would be this mysterious antiderivative big F at t, and we're going to sub in the two limits, a and g of x. So do that with me here. This is going to be the big function, so cap f of g of x minus cap f of a. So cap f of g of x, you might notice in that is a composition of functions. So cap f of g of x is a composition of functions. Now, remember, fundamental theorem part 2, it's a integral as a function. We're going to be taking the derivative of it. So the derivative of this integral is the same as the derivative of this FTC part 1 applied. The derivative of a composition, got to use the chain rule. So that is going to be the derivative of cap f of g of x, which is little f at g of x. But I got to multiply by the derivative of the inside function. So g prime of x. And the derivative of cap f at a is, oh, wait a second. That's just a constant. And the derivative of a constant is 0. So that's why the chain rule is applied. It's really applied in all cases, right? Even back here on the original, we did the derivative of cap f of x was little f of x, but then we multiply by the derivative of x. And the derivative of x with respect to x is just 1, and it disappears. And that's why you didn't feel the chain rule happen, but it happens all the time. So I'm going to show you a few examples. We're going to roll through some examples here where we're finding the derivatives of integral expressions. But we're going to do it with a middleman in between. We're going to use the fundamental theorem calculus part 1. All right, so here I can actually rewrite the integral expression. I'm not even going to worry about finding the antiderivative. Why would I worry about finding the antiderivative? Even though I can, I'm not going to worry about it, right? It's just some mysterious antiderivative at x minus that mysterious antiderivative at 3, right? That is just the fundamental theorem of calculus part 1 as applied to the definite integral from 3 to x of 2t dt. But you notice I am just turning around and taking the derivative of it, right? The derivative of that expression that is in terms of x. So what is the derivative in terms of x, or with respect to x, of the mysterious antiderivative? Well, it's the same as the original function right here, 2t. So that original function, little f of x, is the function 2t, but we're going to be subbing in the input x. So this is just 2 times x. Okay, so next one, we've got another function as from a constant to x. So we can rewrite this integral as mysterious antiderivative at x minus mysterious antiderivative at 5, right? Knowing that the mysterious antiderivative at 5 is just a constant, right? We could spend all of our energies finding the antiderivative, getting an expression that's not outside of the realm of possibility, but what's the point? All I'm doing is turning around and asking for the derivative of that expression that you painstakingly found. It's going to be the derivative of this antiderivative, big F. It's right back to little f of x, and the derivative of that constant is 0. Now, what was the original f of x? The original f of x, the integrand function, is 3 over t plus 1, but now it's in terms of x. The input is x, not t. T's at spaceholder. So we'll say this is 3 over x plus 1 is the derivative of that integral expression. All right, so this one is a little different, and I did it on purpose, right? Instead of being a constant to x, right, that's flipped. Think about what you could do. You could go ahead and rewrite that as the derivative with respect to x of negative, flip the limits, flip the sign. So you could say 10 to x. So you feel maybe a little more comfortable, right? You feel a little more comfortable with a constant to x. But maybe we didn't really have to do that. Check it out, right? I don't really have to do that, right? I'm going to spend my energy here thinking about this in terms of the fundamental theorem of calculus, right? This mysterious antiderivative at 10 minus this mysterious antiderivative at x, right? What is any function at a constant 10? It's just a constant. So that part's a constant. Here I have negative mysterious antiderivative. Now, what is the derivative of that expression? Well, the derivative of the constant is 0. The derivative of negative antiderivative is just the original function f again, this time at x. And what's the original f? It's the integrand function e to the t over t, no longer in terms of t, but in terms of x. So negative e to the x over x is my answer. Cool beans. All right, we're going to try to expedite the rest of these problems. Oh, wait a second. Ooh, this looks a lot tougher. I was getting into a routine there, but this looks tougher. But I can use the same idea here. I want to rewrite the integral in terms of the fundamental theorem, but I'm not going to spend my precious energy finding that antiderivative, right? It's some mysterious antiderivative of 2x minus that mysterious antiderivative at pi. It's mysterious because I don't even care, because what am I doing? What am I doing with it? I'm not just evaluating the definite integral. I'm finding the derivative of it. Finding the derivative of this expression. So why waste my time? That's going to be, chain rule is definitely is up for consideration. The derivative of cap f of 2x is going to be the derivative of cap f, so little f of 2x multiplied by the derivative of the inside function. Now, the inside function is not 3 over t plus 1. The inside function is 2x. So the derivative of that is 2. And then cap f of pi, that's just a constant. That thing is going to, the derivative will be 0. And what is the f function that we were dealing with? Yep, it's just that integrand 3 over t plus 1. But now the input is 2x. So 3 over 2x plus 1 multiplied by 2. You can simplify that. That's 6, but moving on. Okay, another derivative of an integral, this time pi over 4 to x cubed. Again, mentally, I'm thinking mysterious antiderivative at x cubed minus mysterious antiderivative at pi over 4. That's a constant. That's a function. I'm going to be taking the derivative of it. The derivative with respect to x of this quantity is back to little f of x cubed, but then using the chain rule, I've got to multiply by the inside function. And what's the inside function? Right there, booyah, x cubed. The derivative of that is 3x squared. There is a constant. Its derivative is 0. So just to finish it off, what's the little f I was using? Yep, the little f is that function right there. So that will be that function with x cubed subbed in. Tangent of x cubed squared, x to the 6th times 3x squared. There is my derivative of that integral expression. All right. Ooh, this one's different. All right, this one's different, but it's still the same analysis, right? We've got a definite integral here that we can turn, that we're taking the derivative of. Okay. So I'm thinking, okay, mysterious antiderivative at x squared minus mysterious antiderivative at 5x. Not worrying about what that antiderivative is because I'm turning around and taking the derivative of it. So the derivative of cap f of x squared will be little f of x squared times 2x. The derivative of cap f of 5x, notice it's not a constant this time. It's a function of x. That'll be little f of 5x multiplied by the derivative of 5x, which is 5. Now I've got what is that little f I was dealing with? Oh, yeah. It's the original integrand in my integral. So I need to just write 3 over t plus 1 with the input x squared. So that will be 3 over x squared plus 1 multiplied by 2x minus 3 over 5x plus 1 times 5. And I can simplify from there, but that's boring. It's done. Now the problem's over. I'm done with it. It's not fun anymore. Okay, last problem is an application of this idea of derivative of an integral expression. So I've got a function h of x. It's defined as an integral function, right? The integral from 1 to root x. Hey, 3 over t plus 1 seems to be a common theme here. All right, we're going with it. All right, so here is my function h, and I'm asked to find the equation of a line tangent to the graph of h of x. Well, I don't know what that looks like. I mean, maybe I could graph it, but that won't help me. My needs for a tangent line are a slope and a point, right? I need a slope and I need a point. So the slope would be h prime at 1, and the point is going to be 1 h of 1. Okay, so maybe I could get 1 h of 1 first. So 1 h, what is h of 1? H of 1 is going to be the integral from 1 to root 1, derp, that's just 1, of who cares? What is the integral from 1 to 1? It's 0. So I know my point. My point is 1, 0. Now, how do I get the derivative? How do I get h prime? Okay, I'm going to be taking the derivative with respect to x of this integral expression, 1 to root x of 3 over t plus 1 dt. Well, if I run through my routine, I'm thinking FTC part 1. I'm thinking mysterious antiderivative at root x minus mysterious antiderivative at 1. I know this is a constant. I know this is a function. I'm not worried about what that actually looks like in truth because I'm just going to turn around and take its derivative. So the derivative of cap f of root x is going to be back to little f of root x, but then I need to multiply by the derivative of the inside function, which is root x. So that's x to the 1/2. That will be 1 over 2 x to the negative 1/2. So 1 over 2 root x. And then the derivative of that constant is 0. Now, what was the little f I was playing with? The little f I was playing with is the original integrand function, but I need to write it in terms of root x. So 3 over root x plus 1 multiplied by 1 over 2 root x. And I'm going to evaluate that at x equals 1, because that's where I was looking for. I'm looking for the derivative, right? This is h prime of x. So h prime at 1 is going to be that expression evaluated at 1. Which is 3 over root 1 plus 1 times 1 over 2 root 1. Well, that looks like 3/2 times 1/2. That's 3/4. I'm almost there, gang. I got my slope now is 3/4. I got my point is 1, 0. So now I've got to find the equation of a line that has a slope of 3/4 and passes through the point 1, 0. Here's what that looks like. Y minus 0 is 3/4 times x minus 1. I'm done. There it is. Man, that was a good time. See you later, alligator.